Yep.
All right. Thank you all for coming to this first Boeing seminar of the winter quarter. It was supposed to be the second one, but the first one was canceled, as you know. So it's my distinct pleasure to introduce this week's Boeing speaker, Nathan Kutz, from our own department here on campus, the Department of Applied Mathematics. Nathan got his PhD at Northwestern University in 1994, after which he was a postdoc/visitor at the Institute for Mathematics and Applications in Minnesota, Princeton University, and Bell Labs. After that, he came to University of Washington, which he joined as a tenure track faculty member. He's now, of course, a full professor. I should say that he's actually an alum from the University of Washington because he did his undergraduate here. Nathan's research covers very many disciplines. Let me single out a few. He works in nonlinear optics. He works in neuroscience and in very many aspects of data science. He is the author of 3 books and almost 500 journal publications and book chapters. And as of fall 2021, he is the director of the new NSF AI Institute in Dynamic Systems here at the University of Washington, which is funded by a 5-year, $20 million NSF grant. And that institute will actually have its opening event in a few weeks. So,
all right. Hey, great to see you all. I haven't seen this many applied math people in a long time. And it's great not to see everybody on Zoom mute, right, which is how I'm used to seeing a big group of applied math people over the last couple of years. So first of all, you should never predict the future. And so I put this in here. But really, this is more of a reflection of my own little personal applied math crisis. So you could think of it as a sort of introspection around thinking about governing equations, because this is what I've spent my whole career on. Doesn't matter what the application area was. I've always thought about, like, let's take some governing equations, let's start understanding a system. And now, with emerging data science methods, there we go, take that off. There's a lot more flexibility about things we can start thinking about. So what I want to do is maybe just kind of walk you through some of the thinking around what are the possibilities that machine learning data science can bring to the table for us in terms of modeling systems. As Bernard said, this is really in a broader context of what's going on across the sciences. And partly UW has become quite a leader in artificial intelligence, machine learning. And this is also partly what led to this grant, which was this AI Institute grant, Dynamic Systems, which at its core involves 3 main things. One is a thrust towards fundamental machine learning mathematical methods. So a lot of this involves where I love to be, which is dynamical systems. It also involves control, optimization, statistics. These are sort of the workhorses of the theory. And we're really kind of taking these and pushing them out towards a lot of application areas in the engineering sciences. So a lot of that's why the control is such an important aspect of this, as well as really developing out an educational framework for this. So very much a concentration on bringing out open source resources, code, data, lectures, all put online for people anywhere, anytime to be able to access these things. We have a really fantastic team. But first, I guess this is sort of a mission statement. It's way too long to read. But I'm going to point out some key words here. Explainable and interpretable. So staying in the applied math trajectory or physics or engineering thinking, we really would like to build models that we can come back to and start, if we understand them well enough, we can build new systems. And typically, that comes down to our governing equations. This is one of our real workhorses for extrapolating physics. So we would like to be able to do that. We will also be developing ethics courses along with the Institute. And importantly, what we call a common task framework, which is we want to set up challenge data sets. So lots of people can bring their diversity of methods to the table and try them on challenging data sets. So we have a fair way to compare. So instead of everybody saying that their method is the best thing since the wheel, now what we have is a way to really look at that and actually compare it against other people's methodologies. The website's here, dynamicsai.org, if you want to check it out. Here's our team. It's Pacific Northwest centered. So here's the UW team of faculty. We also involve Seattle University for the ethics training. Montana State is involved with us, Boise State, Portland State, Hawaii, Nevada, Alaska. So this Pacific Northwest partners, along with some disadvantaged schools like Harvard and Columbia who need help from better schools to help them out. Oh, is this on tape, right? Okay, that's right. No. So we go. It's a really great team of people. And as Bernard said, we're having our kickoff. Here it is, March 16th and 17th. If you go to the website, pretty soon we'll have a link to, you can actually register for it now. It's going to be a hybrid. There'll be an in-person component or online. We have a fantastic group of speakers. Everything will be put up online as well afterwards if you would like to check it out for yourselves. So almost all of this institute is starting to think about how do we take data and build models. Okay? Now, that's nothing new. We've always done this. And in fact, where I want to kind of start with this is starting to think about where our research has gone. A lot of this research I'll be talking about is joint work with Steve Brunton. And really I want to feature a lot of the work of students and postdocs that have come through applied math and mechanical engineering and different departments here. So what you'll really see is a highlight of their work in this talk. And so when we start thinking about building models from data, I'm going to highlight that there's two things that I at least want you to have in your mind when we do this. One is an appropriate coordinate system, and two is, once I get that appropriate coordinate system, to build a dynamics model there. Okay? So coordinates and dynamics, the pairing is there, and I generically represent this like this. I'm going to take some data from some measurements, and I'd like to figure out how to make a transformation into a new coordinate system, solve the problem. This is the workhorse of applied math. This is what we do professionally, right? Is a lot of times when we solve problems, it's about the right representation or coordinate system and then solving it in that system. Nothing different here, except for you can already start to see that I'm going to start leveraging the power of machine learning tools to help me out with this. I don't want to use machine learning in an end-to-end fashion. I want to use targeted use of these neural networks so that at the end when I build these things, hopefully I can actually extract out some meaning and some interpretation. I want to walk through an example of this, what I mean by this, in very simple language and terms. And then we'll go and start solving some problems with it and start seeing how we do this in sort of an automated fashion. So what you're looking at here, this was on my opening slide, is the night sky, and which is obvious, I suppose. But here, this is the path of Mars. So this is the retrograde motion of Mars. This is Saturn over here. So I love this picture because it shows you, in some sense, what was the oldest of all physics problems. Celestial mechanics was what really was physics for a millennia and a half. Okay? And in fact, for much longer than that even, we were trying to explain the motion of the planets. Could you predict the pathways? And the ancient world certainly was interested in this. And the ancient world believed there were 6 planets. They were named after the Roman or Greek gods. And their pathways dictated the course of human life in some sense, right? And so understanding the paths would be very important. And so the earliest theory about how these pathways actually worked was the doctrine of the perfect circle. It's unfortunate the projector is so poor here, but this is a beautiful Renaissance painting really depicting this idea that to map out this retrograde motion, you could think about it as the motion of circles on circles. Or, in our language, we might say this is the earliest version of a Fourier transform. Because to describe the planetary motion, all you had to do is describe the circles, the period of rotation around that circle, and you could construct these planetary orbits with very few small representation of frequencies. Okay? So that was the doctrine of the perfect circle. It came out of Alexandria, Egypt in the 2nd century AD. Claudius Ptolemy. That's the earliest we know about this written down. Now, it took a millennia and a half before we finally moved on from this theory. It was very successful. And the way we moved on from this theory is through a coordinate transformation. And this was a very costly coordinate transformation. Costly in terms of the impact on the scientists' lives who actually really took it to its conclusion. Galileo and Kepler were the two that really laid down the mathematical frameworks to put this on solid footing. Copernicus, of course, was was really advocating this idea, but it was really the observations and the mathematics of Galileo and Kepler that allowed us to move from the Earth-centric coordinate system to the heliocentric coordinate system. And in fact, the way they just explained it is, well, the reason we see the retrograde motion is because Mars and Earth are both on orbits around the sun. Okay, and that's why we see this retrograde motion. Now, why is this coordinate transformation so important? The reason this coordinate transformation is so important is because once you're in the right coordinate system, about 100 years later comes along Isaac Newton, who is able now, within that coordinate system, to posit the inverse square law of gravity, and F equals ma, and now you have the coordinate system to go along with your physics model, F equals ma, right? That was a transformational theory that really set off the scientific revolution and gave us a lot of new insight into how physics actually works. And of course, here's what's interesting. As we got better measurements, it came down to this. We built better technologies for measuring more precisely the orbits of the planets. There was an inconsistency, discrepancy between this F equals ma model and what we actually observed. The first thought is we're missing some planets. To predict where they might be, they're not there. And in fact, the discrepancy was not from other planets. The discrepancy was from a failure of this model. And then you have, in the early 20th century, Albert Einstein proposing general relativity, which is a new model of space-time curvature, which we only could access to it through this better measurement technology. Okay, so the data has always driven our modeling capabilities. And the limits of our measurements have always been able to take us to this next level of building models. What's exciting about now is really the star of the show, of the data science show, is sensors. Sensor technologies. Sensor technologies often are built on lasers. You can buy lasers for $1. Isn't that amazing? Only a little more than 50 years old technology, and now you can buy these things for $1. And what do you do with them? Now you measure all kinds of things with them. Same thing with your phones, right? Well, my phone doesn't have really good camera because it's an iPhone 7, it's super old. But some of you that have the new phones, right, you have like way too high a resolution front and back, right? Like 4K front and back cameras. These are all, in some sense, sensors that allow us to collect data to essentially now improve our modeling of the world. So let's talk about modeling then, because this little planetary history of modeling is kind of interesting, I think, from a framework of the following, which is one way to model this is just simply to say, well, here's how I could use this architecture. I could take images of the night sky, which is just a 2D projection in my world, and say, all right, there's the image. What I want this transformation to learn is something where I could learn this Earth-centric coordinate system. In other words, here I could learn that the orbits, I could just come up with a set of frequencies and reconstruct the planetary motion. So this is the Ptolemaic view of how this circles on circles would work. So this gives me a prediction engine, and it was very successful. Okay? And it's one way to model this system. And it's one way to use that architecture to do so. Another architecture to do this is exactly what I talked about earlier, which is what if we instead transform the coordinate system? In other words, I want the work of this neural network is to understand from this picture to move me into this coordinate system right here, the heliocentric coordinate system. And once I'm in there, I want to learn this law. So I want to learn a coordinate transformation that sets me up to have a very nice representation of a physical model. And by the way, notice that I have a pathway back to the original system. So I come in, and there's the inverse of this transformation, if you will. Okay? Two different paradigms. And of course, there comes this question about which one should I use? And this is partly what we're going to consider. And I also want to have this discussion around Kepler and Newton, because in some sense, in a basic way of thinking about this, Newton comes up with F equals ma, and the solutions to his inverse square law are the ellipses that Kepler had written down already. So you can always ask the question, so what did Newton bring to the table that was more interesting? Because he made up this thing called calculus, and which could seem like just a convoluted way to get back what Kepler already had. But the big difference between them is what Kepler was doing was interpolation. In other words, he had the observations. It took him 11 years once he got the data from Tycho Brahe to publish his results. He had no MATLAB, no Python. Like, this would have been an afternoon of work, right? 11 years hand calculations and regressing to get this right. Produces these elliptic orbits, but here's the difference between them. With F equals ma, what can you do? Yes, you can reproduce what Kepler had, but now you can do something much more interesting. You could imagine launching a rocket from Earth and putting it in orbit around the moon. Never seen that data set. I'm completely in an extrapolatory regime. This is the big difference about governing equations. Newton gives you the power to extrapolate. Kepler does not. Okay? And at least for the planetary orbits, they both give you the same result. It's just when I want to move outside of that data set, I clearly want the governing equation angle on this. By the way, the legacy of Kepler and Newton is alive and well today. And here's where I like to think they live. These are two of our grand challenges problems of today. Both autonomy. Robots, cars. Right? Both intelligent agents moving in an environment. And there's a big difference in how we've gone about building models for them. By the way, you can see this is quite remarkable. This is out of Boston Dynamics. I think it came out sometime last spring, this robot being able to do entire gymnastics routines. As you know, I broke my neck about a year ago, and I would re-break it if I tried this floor routine that this robot had here. So you have this remarkable features, and this car just is driving around. And there's a big difference in how they've been built. This is a physics-based model. The masses of the arms, angular momentum, all of the physics is imbued inside of that robot in order to navigate its environment and stay stable, move through new environments. It has essentially extrapolatory physics on it. The self-driving car is a bank of sensors with a ton of labeled data. It knows no physics. It has some rules about speeds it should go, what to watch out for, where to stop, but it's not a physics-driven instrument. This lives in an interpolatory world. This can potentially go to an extrapolation. Okay? By the way, one of the dangers of this is that if you have something that wasn't in your data set, you can kill people. Now, this is actually a real problem here. Happened in Pittsburgh 3 years ago, I believe now, where a woman was hit because she was running on the side of the road with her bike on her shoulder. That wasn't in the training data set. The self-driving car was forced to make a labeled decision about what that was. Now, we as people would recognize that immediately. As a person running on the side of the road would drive around. This got labeled as a bag. So the car was told, well, if you see a bag on the road, you don't hit the brakes for it. It's dangerous for the passenger, so you go through it. That woman was killed, right? Because that wasn't in the training data set. Now, that incident will never happen again. Why? Because now they'll have 5,000 training examples of a person running on the side of the road, and so now you've closed off one piece of the interpolatory gap, right? But we don't know if there's others out there, right? That's one of the problems. I don't want to make too much value judgment about either one of these. They're both very successful paradigms. But I want to live up here. This is where we're going to stay for the rest of the talk. Okay, so let me set up a mathematical framework around what I want to do with this. One is I want to take data measurements of the system. Now here's the way I'm going to frame this, is I have measurements of some system where I don't even know necessarily what the state variable is. Right? I just take measurements because I have some kind of measurement device. I have a measurement model H that maybe maps me over to the state space. The state space itself is evolving according to some dynamical system. Okay? Here's what I don't know in this setup. I don't know what the dynamical system is. I just, let's say, record from sensors. I don't know F. I don't know the measurement map. I don't know X or H. So this is an terribly ill-posed problem. Okay? In grad school, I was allowed, if someone said a problem's ill-posed, you didn't work on it. You went and worked on something else, something that was well-posed. But now, you guys don't have that luxury. Your luxury now is to say, well, if it's ill-posed, how am I going to solve it? What you're going to do is now start placing regularizations and constraints on this. That's how we solve these ill-posed problems now. You say, okay, let's come up with some extra constraints, conditions, regularizations, they're called, in the machine learning, and we're going to impose those until I make it well-posed. Okay? So what kind of constraints do I want to put in this? Here are the constraints that we're going to bring to the table. Interpretability and parsimony. So this gets us back to this idea of governing equations. Governing equations have this parsimonious representation. You can represent very complex fluid flows with the Navier-Stokes, which just is a very nice compact representation, and has some interpretability aspects to it. So for us, it's all about going after these two aspects in our model building. Of all the possible models we want to build, I want to promote these ideas. But by the way, these ideas go way back. William of Ockham, in fact, when we started to relearn out of the Dark Ages about Aristotelian logic, it was William of Ockham who was the one saying, you know, look, we should start building these nominal models because people were getting very carried away with building these logic constructs that were what he thought were way over-parametrized in some sense. So he really went after sort of a more succinct nominal representation, and really we're building on this same idea here. You see it in other people like Pareto, who we have this thing called the Pareto front, which is out of all these models, which one is sort of, in some sense, the simplest yet most predictive. Right? We balance these two, and we call that being on the Pareto front. Okay, so we want to start bringing in these concepts here into our design of taking data and building models. And this is how we're going to make well-posed models out of this. So it's not just the number of terms, it's also the number of dimensions. And we want to be parsimonious in both. So let's talk about then this idea of model discovery. And I put here a question around finding governing equations because this is actually what I want to address with you right now and what the theme of the talk is. What is our actual goal? And I want to walk this through in terms of a simple model that hopefully maybe many of you will see next quarter, maybe you've seen it before, which is the Burger's equation. So here's Burger's. We're going to call this our truth model. Now, Burger's was the first nonlinear PDE I saw. Okay? So it's kind of our canonical, often we study shocks breaking and stabilization of shocks through like diffusive regularization, or you can also put in there dispersive regularization and get KDD out. But you know, here we go. This is some regularization on this term here, which is sort of a Burger's term. So let's think about this PDE. I give you this governing equation. Now, if you get a governing equation like this is where we sit as applied mathematicians. What is our goal? The entire goal, okay, so there's a bunch of you who are either far along in grad school or just starting. What is the point of our courses? The point of many of our courses is to take this and figure out how do I solve that. So having the governing equations is sort of your start point, and then we teach you methods to try to crack that nut to get out some meaningful representations for solutions. So let's talk about this process. When it comes to Burger's, there is this thing called the Kohlhoff Transformation. And there's something magical about this because this Kohlhoff Transformation here, if I switch from my original variable u to this new variable v defined by the Kohlhoff, I actually get a linear model. So there's two advantages here. One, it's linear. Two, there's only two terms instead of three. So one might say this is a much better representation, or more convenient for me, than this original nonlinear PDE. So I used a coordinate transformation to take me from a nonlinear PDE to a linear PDE. But by the way, once I write this down, that's not really what I want, because then we still have to solve that. All right, let's go solve it. Here's just, for instance, if you have pin boundary conditions on 0 now. Here are the exponential solutions you find. Right? You write this thing down as an infinite sum of Fourier modes, space, and then your exponentials in time. And by the way, we still wouldn't really use this. I mean, we'd write this down on paper as 1 to infinity. But of course, we'd never really do that. We'd actually do this, sum to some finite value. Okay? So all this here is a pathway, let's say, of applied math education. And if I were to actually sum this up at different points in time and space, this is maybe what it would look like. Okay? So here is a representation. Here is a representation. Here's another representation. And then, by the way, there's just this, the data itself. 4 different representations that you have available to you for the same phenomena. There's another way to go with this, which is I could also just represent this instead of as a PDE, as an iteration scheme. Right forward in time. This is just simple finite difference discretization of the system. This approximates this. I could actually just put this in a loop and then get back to this again. So what I want to highlight here is, 4 representations that I have available to me for this system. One is the governing equation itself, which, by the way, if I gave you the governing equation, the first thing you'd have to do is go actually solve it to get me solutions. So what if I just actually learned this instead, directly? Or even the linearized version, which was the heat equation. Or I could even learn the stepper, because I would have data like this. Okay? So there's these 4 different ways to do this, and then now what I have is a tool in these machine learning technologies that gave me great flexibility to learn different representations. I could learn governing equations, but if I just give you a governing equation, you're just going to have to go solve it. Why don't I just give you the solution directly? Learn that directly. Okay? All right. So the way I like to also think about this is, in the suite of representations, how should we start thinking about this? And here's my little analogy that I came up with. Let's see how it sits with you. Okay. Here's how I think about a governing equation now. It's like DNA. It sort of encodes everything about the truth. But if I tell you and ask you, well, yeah, but tell me what the solution is at this position and at that time, you can't tell me that from there. You actually have to go solve it. You either have to go get the solution to tell me what the solution is at a point in time and space, or simulate it. In other words, you have to produce this. This here is interesting because you can go interrogate it and tell me where for a given space and time, tell me the actual value, but it's very hard to draw knowledge out of this. So the way to think about this is your DNA, and if I ask you then for from DNA, you could say, but what does a human look like? I'd have to grow this for 18 years and produce a human. And subject to boundary conditions, initial conditions, it would come out different. That's our environment, right? So you have a nature and a nurture angle on this that would produce all these different humans, and it takes me a long time to go from here to here, just like, okay, this is not very computationally sophisticated, I understand. But hopefully you get the analogy, right? But if I give you this, in some sense it's a nice abstraction, but it's meaningless when I say, give me an actual value. I actually have to have this. So there's different ways to think about encoding this in terms of a representation. So there could be advantages of representations where I just give you back the solution, not the governing equations. So let's start talking about how would I train for these different objectives. So let's come back to the mathematical framework. And here's my framework that I have. I'm going to learn from the data a measurement model to a state space with some dynamics. And now I have some choices to make about the kind of dynamics I want to learn. So let's talk about some of the choices I can make. How about a linear model? So in some sense, I want to take the data and just go right to learning a linear model. In some sense, skipping the governing equations and learning the Kohlhoff directly and say, here's the linear model that best represents the data in the right coordinate system. And this work really started a lot with some of our Kokoman Theory work that we've been going on. In fact, there's going to be a nice SciAm review article that kind of reviews a lot of the Kokoman Theory for modern dynamical systems. It's up on the archive. You can read it. But this work started back here with Bethany Lush. So Bethany is now at Argonne as a machine learning person there. And here's what Bethany did. She said, okay, let's consider the nonlinear pendulum. X double dot is negative sine theta x. Okay? So the pendulum usually is thought of as kind of an easy model, but it's not that easy. It's a fully nonlinear system. Normally when people think it's easy, it's because they linearized. Then it is easy. But the full nonlinear pendulum, what I want to do is start with my measurements, try to learn a coordinate transformation to a new variable, and come back out. And what do I want to have happen in the new variable? I want that when I go from time k to k plus 1, and I'll just take some delta t into the future, I want that to be a linear operator, which we know holds for small amplitude fluctuations, but as soon as you get large amplitude, that doesn't hold anymore for the pendulum. The other thing is we want to constrain this to 2 dimensions because we know the pendulum should be able to be characterized as theta theta dot. So it's really easy at this point, if you're in machine learning, just to go to high dimensions in here. Say, go to high dimensions. You can code everything there. That is exactly what I don't want to do. I want to keep this parsimonious in dimension because that's what the physics actually is. I'm going to make it be low dimensional. So the trick to solving this problem was to recognize that, well, the oscillations themselves are parametrized by sort of a frequency, right? If you've been on a swing, you realize that larger amplitudes have larger periods when you start swinging. So what we're going to do is we're going to build this linear operator, but we're going to train a second neural network to learn how to parametrize this linear operator so there's a parametric dependency there, which is essentially related to the frequency. And in so doing, you can actually take this fully nonlinear pendulum. Here's the phase portrait of this pendulum. Here are the oscillations. As you get large oscillations, it becomes quite nonlinear. And here's how we can embed it in a complete linear space, all the way up to the saddle at the top. Okay? So we train this neural network to make the pendulum linear all the way to the saddle. Okay? So that's a nice step, because now what we did is we just learned a coordinate transformation, and here are the nonlinear eigenfunctions that took it to that coordinate. And now I have a linear model for that. Theta double dot is negative sine theta. We can do harder problems. So let's start ramping it up. Let's take flow around the cylinder. So we take flow around the cylinder when we have von Karman's vortex shedding off the back end of this thing. And if you look at snapshots of that, so the full PDE, you find there's a low-dimensional subspace, 3-dimensional subspace that characterizes the dynamics. We took the time series of that subspace, and you can embed it in a completely linear model. So essentially, you can take that flow field, which is a nonlinear dynamical system that went through a Hopf bifurcation, so it has a Hopf normal form. Actually, it's not quite a Hopf. It's a little bit more subtle than that. But you embed it in a completely linear model. Okay? So again, this is like learning these Kohlhoff transformations. I don't have analytic expressions for you, but I have a neural network that learned how to do it. Then we took it even further, and this one is the one that is, I think, the most surprising. This is work done with Craig Jin. Many of you know Craig. He was in the department for a number of years. One of our just an outstanding human, outstanding teacher, really fantastic guy. And we got involved in this project to learn this idea of like how do we embed PDEs more naturally into a linear subspace. And the one that we started with is, of course, the Kohlhoff transform, we try to say, could we learn something like that for burgers? And of course we did. And it turns out it looks nothing like the Kohlhoff transform. And every time you retrain it with a random start of your neural network, you get a different transformation. So it seems to suggest that we have some math to learn still, because there's an infinite number of transformations that can pull off a Kohlhoff. Okay? But then we did something even harder, which is we took the Kuramoto-Shibashinsky equation, which is we had a neural network architecture moving me from my initial measurements to some latent space where I want this linear map to happen. And we were actually able to learn this. This is full spatial temporal chaos in the Kuramoto-Shibashinsky equation. And even in that scenario, you can embed this thing in a coordinate system where the dynamics is linear. Here is, for instance, the exact solutions, the numerical solutions of KS. Here is our neural network embedding. This is all linear dynamics, and you just see that it matches up with the, these are small runs here, but you can do longer runs. And essentially, this linear dynamics holds in this KS equation. So one way to think about it, it's like the inverse scattering transform. So there are many of us here in the room that have, Tom, Bernard, myself, who all come from a background in nonlinear waves where the inverse scattering transform is this very powerful tool for a class of PDEs, which were completely integrable, including nonlinear Schrodinger, KdV, in which you could find a transformation that made it linear. It's like this is early 1970s when you had this AKNS scheme, Abelitz-Kalb-Niels-Seeger scheme written down, class of PDEs where you could actually do this. And it's been since the 70s where we had any kind of generic tool for that, and a very limited class. But this tells you that this very complex equation that has dissipation, all kinds of phenomena, you could embed it in a linear system. So I think that these examples highlight that we still have a lot of stuff to do here that's kind of fun to do it with. Okay? And the neural networks give it to you. So we don't have any theorems, but we do have evidence. And at least the evidence hopefully can drive the next generation of some thoughts around this. Building on that theme, the other thing that we learn in 569, for instance, is Green's functions. I don't know if we're still teaching it, but Green's functions are one of the canonical methods for solving PDEs. Well, they don't work for nonlinear PDEs because the Green's function solution technique fundamentally relies on linear superposition, and nonlinearity breaks that. Well, find a new coordinate system. This is exactly what we do here. This is Dan Shea. Dan built this neural network where he said, look, I have this model, LU equals F. So actually, not LU equals F. N of U equals F, a nonlinear operator, equals some forcing. So what we're going to do is we're going to learn how to transform the forcing and the U to a new field V where this is LV equals F. In other words, in the new coordinate system, it is linear. Just like what I did before. But now that it's linear, I can build the Green's function in this space. And so if I want to solve that, so I have a nonlinear Green's function. So you give me a new forcing, all I got to do is run through these neural networks, find the solution there, bring them back out. So it's a pretty nice technology finding these transformations. In other words, all I'm going after here is a coordinate in this. Okay? And it works. So there's something really nice about these architectures. I've constrained my neural network to one objective only. Find me a better coordinate system. Okay? And it does that. And I'm using all of the things that we typically do anyway to solve our PDEs. I don't have to just warp space. I can also just warp time. So I can learn a transformation of time to make things more linear. So what do I mean by that? So this is work with Henning Lange. So here's Henning, postdoc here. And so what we did is, it's going to look a lot like a Fourier transform. So what I want to do is take my time series and represent it here as a sum of Fourier modes. But two big things. One, I am no longer, unlike the FFT, constraining myself to be on a 2 pi periodic domain or to make these things periodic in the domain. I'm just going to let sines and cosines be in there and just fit the data. They do not have to satisfy periodic boundaries. Second, I'm also going to find the right frequencies. When you do a Fourier transform, right, depending on how you discretize, those are the frequencies you're going to represent it in. What I want to do is represented in some frequencies that I find unconstrained by a periodic boundary. So it's like a Fourier fitting, and you use gradient descent to get it. Okay, so an optimization technique to do it. But we're going to do one other trick. This is an important thing that Henning did. So right here is just a Fourier fitting, but we can do better. Because look, a time series like this, right, if you have these sharp structures in time, it's going to cost you a ton of Fourier modes. Right? Anything that looks delta-ish in time is going to be basically an infinite number of frequencies. So what it said is I say, well, but that still kind of looks periodic. So what if I learn a neural network that takes a time series and transforms it into something as sinusoidal as possible? Right? You can imagine stretching this thing to make it look sinusoidal. It's exactly what this does, and then represent it in terms of a set of sinusoids. Works beautifully. So you could take data that's quasi-periodic. For instance, we did this with power grid data, which is sort of chaotic in nature, sort of quasi-periodic. You have weekly cycles, yearly cycles, daily cycles, but none of it's really that repeatable. And what we did is we trained this neural network, and we look at our forecasting horizon, and we basically, we do great. The reason I like this slide and always put it up, because usually I don't like to put up slides with a bunch of numbers, but a lot of times people have this idea that I think is quite misguided, like, I just throw in a neural net. Neural nets can beat everything. No, they can't. LSTMs, GRUs, echo state networks, these are all sort of your top-of-the-line machine learning for time series data. But look at the numbers. This method destroys those. And partly because we're just using smart knowledge about what we've been doing forever in these neural nets. Okay? So this is kind of more aimed for the computer science people, which aren't probably in the audience, but if they're watching at home, you just got crushed. Okay? So this is where applied math comes in, right? We're using a lot of expert knowledge here. We also compare it against standard statistical techniques, ARIMA methods, time forecasting methods. And so, again, using these ideas are really powerful. And it's nothing new. It's nothing we made up. It's something we've been doing in applied math forever. Just got a little twist on it. And so maybe another way to frame this talk is, how do I use all my applied math knowledge, touch it up with a little neural nets, and extend the possibilities of what I can do? By the way, the great thing about something like this is I can take some kind of PDE like this. Here's the ground truth. This is a full PDE cavity flow. And so this is expensive simulation to run. And what I'm going to do with this is I'm going to take this, and it turns out you can embed this in a fairly low-dimensional subspace, and you just look at the time series of those low-dimensional modes. And of course, they don't look very sinusoidal, but what I can do is just warp them like Henning warps them to make it look sinusoidal, and then I build a simple model. This thing is stable. So as far as reduced order models go, it can basically be all the reduced order models out there. I'm no longer integrating. You just tell me, when do you want the solution? Give me a time, I'll put it into my solution, you're done. And it's stable, has no growth or decay modes. If you build a projective reduced order model off this through Galerkin projection, generically this thing blows up. You have to do all kinds of work to stabilize it, regularize that. Okay? Okay, so that is one method. Build a linear model. In other words, find a coordinate system where exponentials work. Okay? And by the way, that's most of our applied math education, right? At least from analytic theory techniques, is find something so you can put in exponentials. That's your best shot in life right now of getting a solution out. Okay? So we did that in an automated way. Another way to do this is to say, well, I don't want to constrain myself to a linear model. I want to actually take that data, build a nonlinear model, because there's nonlinear dynamics in this. So I'm going to allow it to not have a coordinate system making it be linear. And so we do this with this called Sparse Identification Nonlinear Dynamics, or SINDY. So what SINDY does is I give you time series data. So the assumption here is that there is some deterministic dynamical system that produced that data, or PD. Okay? So if I give you data, time series X, and you know it came from x dot equals f of x, and you don't know what f of x is, well, you could take that x and you could differentiate it. So you have x dot. You don't know what the f of x is, but you have x dot. So this basically comes down to an ax equal to b solve. And what it is The B is those derivatives. I give you the time series data, you produce the derivatives. Here they are. The matrix A is a library of potential right-hand side terms that represents f of x. I don't know what it is, but I studied applied math, so I studied all kinds of models. I'll just make a library of all the kinds of models I've seen. So each column is a potential right-hand side term. And then x, which I'm trying to determine, is essentially ax. So these are the weights of each of these columns. So it's ax equal to b. It's an overdetermined system. And what you want to do is not backslash. If you do backslash or least square regression, it'll say everybody's important. But if you pick up any physics book, how come all equations can kind of mostly fit on a page? Oh, here's your NLS, here's your KdV, here's your Schrodinger. The idea is, out of this whole collection of library, there's only a few terms that matter. If you believe in dominant balanced physics, then you would believe that there's a few library elements that would matter in this. So instead of solving x equals b through least squares, you solve x equal to b and promote sparsity. L0 optimization. Typically, L1 is a proxy for that. But here, we actually do something like L0 using least square thresholding. And when you do that, here are the terms that are non-zero. They're exactly your Lorentz terms. So I gave you time series. You told me what the differential equation was that produced it. We can do this more broadly for PDEs. Here's a bunch of PDEs. This is work of Sam Rudy. So Sam did this for PDEs, and here's all these canonical PDEs that a lot of us study in our first and second year of grad school. Okay? From nonlinear Schrodinger, KdV, Kermode-Shivashinsky, reaction diffusions, Navier-Stokes. And so I just give you the spatial temporal data, and from that you find these governing equations. Okay? So this is around 2016, 17 when we sort of developed this. And what we've been working hard on since that time for these technologies is to make it more robust to noise. Everything here is based upon producing good derivatives. Good derivatives are hard to make when you have noisy data. So we've had a lot of work progressing that, and the most stable methods available now is to use a weak form of the solution, as an integral form of the solution, and do a statistical bagging trick to find the best derivative estimates. And by the way, all this is built in to this PyCindy package that we just put up. So you can download it and play with it. Tons of examples in there for finding PDEs. Okay. By the way, the one thing I swept under the rug there was when we talked about finding those models is I actually gave you data which was the correct state space. But I started this talk saying I don't know what the right coordinates are. So let's get back to that. And I want to highlight the work here of Kathleen. Kathleen actually works a couple miles over there now. But Kathleen, this is a really great piece of work I think Kathleen did. So I like to call this work sort of GoPro physics. You're going to go film physics. And what you're going to do with that is try to build the model directly from there. What do I mean by that? Well, here's this structure I showed you at the beginning. I'm going to take in my data. And here, for instance, let me film a pendulum. So I give you a video of a pendulum. Now, you and I both know the pendulum. You can look at it and say, because you're biased in your training, to know the pendulum has theta, theta dot as its coordinate representation. But what this has is pixel space. This is a bunch of pixels. It doesn't know anything about theta or theta dot. So what we're going to do is see, can it learn a transformation to a new variable where we're going to enforce the Cindy architecture. And here's what this does. And not only learns it, but it says, okay, I will give you a coordinate system, and it gives you back theta, theta dot, and it gives you in here, theta double dot is negative sine theta. So it not only learns from the video what the right coordinate system is, it then gives you back the governing equations. Okay? That's a really, for us, that's a super important step for the following reason. Where do we want to take some of this? We want to take some of this to biology, where you don't know what the right coordinates are necessarily. right? So a lot of F equals ma physics, we kind of know what the right coordinate system is. You don't need all this machinery ahead of it to tell you what it is. But there's a lot of models out there where that's not the case, and you need the machinery like this to help you even decide what are the right variables. And this is the kind of art technology that allows you to do this. Okay. By the way, you can go beyond governing equations. You can even say use the same technology to learn normal forms. You have some parametrically dependent system walking through some bifurcations. We know that a lot of bifurcation structures, we can locally embed normal forms, but this allows you to build global embeddings of normal forms through the coordinate transformation you have here. This was work with Manu Kalia, who was, I was going to say he was a visitor to the department, but he came for a week. Guess when? February, I know you guessed it right. February 2020. And he got here, was here for a week, and he turned around because of COVID and went back home. That was right before everything got locked down. So, but we continued on this project, and you can see there. So you can just directly learn normal forms. You can also do here with Jason, this is with Jason Bramberger, who's now at George Mason. You can also learn deep conjugacies, Poincare maps. Everything that we've done in dynamical systems, you can just tell the thing to go learn it. Right? So in other words, here's a flexible tool that you can pick up Wiggins' Dynamical Systems book and say, oh, that's interesting. You could probably build a neural network structure around it to help you out. Because a lot of what we learn there are local linearizations, where this says, oh, actually, I can make that not just hold in a little ball. I can make it hold in a whole global regime for you. So that's kind of the power of what these learning mechanisms can do. You can also do things like coordinates for boundary value problems. So I've been talking about dynamical systems the whole time, but there's nothing here. Dan Shea showed that you can actually learn boundary value problems with this just as well. Okay? So all the mathematics comes through for boundary value problems just the same. So again, just to highlight, this is the discovery paradigm. This goes right back to sort of my early slides. Think of this as, here is my input data. And remember, what I showed you was the night sky. So you could say, that's my night sky. The thing what this thing is supposed to do is say, learn a coordinate system. So this is like learning my heliocentric coordinate system, and then from there, learn to write physics. Okay? So that's how you're training this thing, is all the pieces are things that we've just always done. It's just that you're using this as a really powerful tool. Another issue I want to bring up then with this. I've acted like you knew nothing. What I mean by that is I said, you just take data, you don't know anything. But the fact is, many systems we measure, we actually have quite a bit of knowledge about. You might know things like there's conservation of mass and momentum, and there's some kind of pieces of the governing equation you know have to be true, symmetries that hold, Lagrangians, Hamiltonians. So here's some work with Cardi Kohlhoff and Megan Evers. And what we started looking at is, okay, instead of starting from scratch, as if you didn't know anything, why don't instead you say, I have some idea of some of the underlying dynamics. So I know, for instance, that this is true. I have some parts of the model that I know are true. I can derive them from first principles. But when I look at those first principle models and I actually measure it against data, it's like they're different. They don't match. They're off. So what I really want to do is learn the missing physics, the discrepancy. So this architecture is kind of trivial to handle within our framework, because all you got to do is say, well, I know this. I gave you the time series, so you can commute the derivative. Just take the f of x, move it over there, build a library of unknowns, potential unknowns. Everything follows through just like it did before. So this gives you a really powerful tool where if it's difficult for you to derive that missing physics, you can sort of use this architecture and say, well, that's what I'm going to go after. This is true. All I'm missing is something. Go get it and try to get that together. Now, where this plays a really critical role is in these emerging technologies of hopefully you guys have heard the word digital twin, right? This is just an emulator for the physics model. So what you want to do is like build an entire Boeing factory floor, which is a digital replica or simulacrum of the real thing. The problem with it is when you build this model, it's built on a Platonic model of the physics. Here they're perfect. When in fact, each of these joints stick, and then if someone oils it, it sticks differently. And for precision manufacturing, there's no way this model actually captures that correctly. So what do? Put sensors on here and have this thing learn the missing physics that's from here, so that you can actually have this be actually a really good digital twin of this. This is actually a really important problem at Boeing, and one they've had a lot of problems with, because their models that are in the CAD are simply not good enough for them to put it in a real production line. This gives you a pathway forward to that, to get that. I'm going to finish off on, detach myself a little bit now, and just go straight up neural nets for a bit. So you know, I don't know if you've noticed, but I've refrained from doing that. Like I've used neural nets in targeted ways to help me, but it's still contextualized in terms of physics I know, or the models I know. So now what I'm going to do is start saying, well, what can I do if I just pull back a little bit completely from that? And I'm going to talk about two different models. One is from Yuying. Here's Yuying right here. Always a smile on his face. That's what I love about Yuying. He always comes in the office, always smiling. And if you want to see this in detail, he'll be defending soon. So you go to his talk. So here's what Yuying did. We took a multiscale problem. Multiscale problems are really difficult because it's hard to sometimes disentangle all the physics. And if you're doing numerics, you've got to resolve the fastest scales to get the core scales right. So what he did is he said, well, how if I just learn a hierarchy of flow maps? So from dynamical systems point of view, we know what flow maps are. Just how do I go from t to t plus delta t? So this is the generic conception here. And so what Yuying did is said, I'm going to learn flow maps that learn how to step over really big scales, intermediate scales, and small scales. And I'm going to tie them together. So my objective function is I have to have this all work in unison. In other words, the small steps have to respect what's going on in intermediate and large steps. And so you take this training data, and what you can do now is build essentially a time-stepping model. And now this is not constrained by Taylor series. Like if you look at what you do with Runge-Kutta, right? This is a Taylor series expansion that bounds your error at order delta t to the fifth per step. Right? So it really depends on how big your step is. Here, we don't have theorems or proofs about this, but this thing here, for training, you find for the same delta t, it's actually way more accurate than a Runge-Kutta stepper. I'm only going to say that sort of in an informal way because we don't have any proofs about it. It's very difficult to prove things with neural nets because there's these nonlinear transformations. But what this does is if you want to walk way out into the future, you take these really big steps. So you overcome the stiffness issue. You walk way out to the future with the big steps. And then when you get close, now you refine your steps to get to your point. Works beautifully. And in fact, here's some things. We can do not just PDEs. Like here's, again, here's the ground truth, the KS equation. Here's our method. And by the way, I love it again. We crush all these standard neural networks. Okay? But here's like a music score. Rebuild it. These don't. Flow around the cylinder. Here's a movie frame. So this training procedure allows you a very flexible framework. Now, I know what I've given up. I've given up interpretability. But what I've gained is this ability to overcome numerical stiffness issues. And also generalize it to things like this is a movie. There's no physics there, right? This is just a set of images that I would like to reconstruct nicely. And then the final thoughts here is with Xiaowu Pen, which is, this goes back to my analogy around governing equations are like DNA. If I ask you for an actual value, you can't give it to me unless you go solve it. But then if I actually, for instance, some of these are very expensive to run, some of these computations, right? So you're going to run a big simulation, let's say for these multiscale physics problems, very costly. Now I can give you a number. And what Xiaowu did is something interesting, which is a hybrid. It is a model compression framework in which you train a hyperparameter network. So you basically map your space positions to the actual solution of the field, PDE field, called ShapeNet. There's a second network talking to it where you put all the other factors, parameter dependence, time, sensor locations, and you train this neural network. And what's interesting about this is once you've trained this with, let's say, again, very costly to train neural networks in terms of data requirements. So let's not kid ourselves. You need a lot of data to train these. But once you've got these things trained, what you're able to do is produce this amazing sort of hybrid where you say, I need to produce, for instance, here's full turbulence data from the Johns Hopkins data set, turbulence data set. This is very expensive. So every time you go to download data, it's like it just blows up your machine because it's like it's very high dimensional data sets. But what Xiaowu can do is basically put this in this massively compressed framework where if you want to reproduce this, you just tell me at what locations and for what time I'll reproduce them on the fly because this thing here is a nonlinear compactifier of all that information and I can generate all this data back for you in a very compact footprint. So it's kind of almost ideal because what I can do now is I can carry that around on my iPhone and reproduce flow fields on the fly that are massive because they've all been compactified in this representation. So I've moved away from a governing equation, but the gain I have now is if you ask me, I want a flow field over 10 seconds in these locations for this parameter value. I say, okay, here it is. Put those numbers in there, reproduce that data on the fly. So these are all sort of these architectures. And my hope here, this is the end of the talk, is that, you know, what I've really relied on all the way through is to try to bring down things into some compact representation taking advantage of something. I've done nothing more or less than what we typically do in applied math, except now I have a new tool for doing it. I allow these neural networks to help do some of the heavy lifting in terms of finding me a coordinate system or in terms of compactifying things. Okay? And it's a very powerful framework. It allows you to do quite a bit in this model space. The only thing that I haven't talked about is the idea of how do you bring these into control, because that's one of the things that the AI Institute is going to spend a lot of time with. And we've certainly have quite a bit of work in that direction. But at least for here, my hope is to say everything you've learned in applied math or will learn in terms of these classic canonical methods played a role here. All the knowledge I gained from applied math just got built into these neural nets. And so my hope is for you to see that that's exactly where we as applied mathematicians can really shine, I believe, going forward into the next decade or two, because we have the skill set that, at least for physics problems, are going to help us be more successful than just black box training. So anyway, thanks for your time, guys. Yeah, and I guess I'll take questions if anybody has any. Yeah.
Is there any hope for provable accuracy or convergence?
Yeah, actually, that's another great place where I think applied math will play a big role. Is there's very little, let's call it, on the technical side of proving these results, these representations with these nonlinear transformations, which are these neural nets. However, there is a massive growing community in this direction who want to be able to, basically bound or understand these approximations in a rigorous level. I think that's going to be a really exciting field because clearly what we're showing is this stuff works. But clearly the way we prove it works is through cross-validation, which, it's not that rigorous, right? Hey, look, a training set with hold, it works, right? And you move on. But I think this is where I think we're going to have some hope. And I think actually the big hope there is to use a lot of asymptotics. I think we're going to start using this by saying, how about if we consider these nonlinear transformations as near identity? In other words, linear plus a little epsilon, and then try to see if I can get bounds on how those nonlinear corrections work. So I think that's going to be a really big field moving forward for the functional analysis crowd to go after. But there's not that many guarantees right now. Yeah, Tom?
In the ISP comparison, is there any interpretability in that transformation?
Yeah, that's a good question. So let me come back to it here. So here's the thing that bothered us, or what we were hoping. We started this thinking like, okay, for sure, we think we can probably pull out Kohlhoff. Like, can we just train it and learn Kohlhoff? That was our actual goal. We were going to stop there because I thought that was going to be a pretty good achievement. So we were able to do it, and then we were able to do this one, which kind of was amazing. But the thing where we held back from this a little bit was the Kohlhoff we can write down. And whatever we got out of the neural net, it changed every time we reran it. And so it just seems to suggest there's infinite number of Kohlhoff transforms that all can work in there's latent variable space, infinite number of them that allow you to make a linear thing happen, which is kind of interesting, right? Because it could be something where we could come back and say, like, how do I understand that, right? Just take Kohlhoff, and can you understand why there is either a one, I mean, it could be just one linear transformation that's invariant underneath there, right? So it could be something as simple as that, or it could be something harder. We don't know. I think that one is completely open. And this just came out not too long ago, so it's and since Craig left, we've been doing other things. But this I think this one's quite interesting and tells us that there's a lot more PDE math here to be understanding for ourselves. Yeah.
In terms of the linearizing the system all the way up until that settle point where it can't be linearized anymore, I just wonder if you have any insight into like stitching together to create topological features, and if anything about non-integrability of those systems. Is there any insight that has come out from these developments?
Yeah, so one of the questions is, so for instance, here I talked a lot about the Kokoman embedding. So how do I frame a coordinate system to make things linear? But if I write down a linear system, how many fixed points does it have? One. But we know in some of these PDEs we have multiple attractors. So really, to your point, Zach, right, the idea is that if you have n attractors, you need n linear embeddings around each of these fixed points. How we stitch them together, there's some work by Kurzweil. Rich Kurzweil, he's at Cambridge, where he did some of this stitching. He was showing how basically you can stitch one model near one fixed point to another model at another fixed point, patch them together. So there's work starting to go in that direction. But currently, that's exactly what you have to do, is you have to say, I have to figure out how to transfer from this one Koopman operator to another at some point, right? So I can model multiple attractors. Yes? Yeah. This is sort of completely uninterpretable. It just moves you from here to here, but this is like just this math, a bunch of weights and biases in the neural network. And so you could take a field and look at it in here. But it turns out if I just retrain with a whenever you train these neural nets, it usually gives a random start to the weights. You retrain, you get something totally different looking in here. So it's not even, part of the reason we actually did in one of Dan Shea's papers show this. It's like, here's 10 trials. Here's the right coordinates in 10 trials. They're just all completely different. So we lose a lot of interpretability, but we have a linear operator whose eigenfunctions and eigenvalues we can look at. And that becomes pretty valuable, especially the eigenvalues. The eigenfunctions maybe not as much because the coordinate system keeps changing, but the eigenvalues are very informative. So non-interpretable, but linear. Yeah?
Do you at least see the same spectrum every time you retrain it?
Yes, I believe we did. Yes, I think that's the, so the spectrum, yes. I believe that's right, yep. Anyway, it's kind of interesting, right? So if you do PDEs, you're like, we're used to like, there is one representation in the linear, like it's a unique representation in these when we kind of usually embed it in our Fourier modes or whatever we have. But here it's like, well, I can do it any way I want. That nonlinear transformation is, like again, I think there's so much we have to still learn about nonlinear transformation. Especially, there's one other part that's special about this. It's a compositional nonlinear transformation. It's not just a nonlinear transformation. It's this composed structure, right? It's functions on functions. And I don't know that much about compositional math, but I haven't even seen that many people that do know much about compositional math. But that seems to be driving this whole thing. So I think that, Tyler, I think it goes back to your question. I think it's going to be very interesting to see the future of where people do analysis on compositional maths, because so much of this is sitting in this compositional structure. Yeah.
Can you talk a bit about sort of the lessons learned behind how to build out these neural networks and the neural net for the architecture and the application?
Yeah. Okay, let me just be super blunt. Mostly the lessons learned is that you have to be prepared to fail again and again and again and again. You have to have patience if you want to do this stuff. The number of times, everything I showed you here, so this is the big lie about deep learning. Oh, look at this, this works amazing. Except for they don't tell you how many times they failed to try to make it work. And we did this repeatedly. And so whenever we do neural network projects, one of the things I always emphasize to everybody is like, okay, you have to be prepared to go through the desert. Because your failures don't even tell you what the next direction is. Oftentimes when you try a method it doesn't work, you sometimes gain insight, like, oh, I should have done this instead. Here you just fail, and it doesn't give you any gradient towards the right thing. So you just keep trying things, and eventually you get yourself in that right parameter regime with the right architecture, things work. So this goes back again to Tyler's question. There's a lot that we have to learn about even how robust these trainings are, because they don't seem robust at all. The power, by the way, of Google and Facebook is they can just simply say, well, I'll just throw this up on 1,000 GPUs. Try them all in different regimes, see what works. And here, we don't have that option. We have one GPU now through the department, right, over on the HIAC. We bought another through the AI Institute. So there we go. We got less than this many, right? And Google can just say, I don't care. Just computing for me is like an infinite resource. It's totally fake for the rest of us. Yeah. Yeah. Okay, so Hod Lipson, who, if you ever just Google him and watch a talk of his, he'll be one of the best talks you've ever seen in your life. Hod just put up a paper. He's part of the AI Institute. He'll be here in March giving one of the keynote talks. Hod just wrote a paper where he said, okay, suppose you're an alien from a different planet and we're from Earth, and we both come together, we don't speak each other's language, nor do we know each other's mathematical developments. We're having an interaction over a double pendulum. And you ask the question, what's the right representation of a double pendulum? Now what we'd write down is theta, theta 1 dot, theta 2 dot, and we'd write down our equations. The question is, there's nothing unique about that. So what he did is he took data from a video, did the same kind of thing here. He said, okay, can I find a coordinate transformation to embed this? And what he finds is, every time you rerun that neural net, you get a different embedding. They're all four-dimensional, just like the one we wrote down on Earth. So you have an infinite number of ways to express that. Why is ours right? Or what we think is right. So there's infinite valid ways to do it. So becomes this question is, what are we doing as humans that we say, when I write that down in terms of our coordinates, that we think it is more right than if you were to write it down as something else? So going to your question is, could we, for instance, in here, start enforcing things like, I want smoothness. I don't want just the first derivative to be smooth. I want the second derivative. How many derivatives can I enforce to be smooth? or I want some kind of properties there. So in other words, here is where if we did more regularization, we might eventually force this thing out of the infinity of solutions to the one that we think of as the the human representation. I think it's going to be fascinating to try to do that as we go forward in time. But right now, it just says, I can do this in an infinite number of ways. Which is kind of remarkable, because I can't find a single one. Right? I can't find a single way to do this, and it finds an infinite number. Right? So there we are. Computer 1, me 0. So. Yeah, so the question is, in that last example, this does compress it, but if I look in here, it's not interpretable to me yet. But the question is, could I enforce some regularizations here to try to have it be interpretable? And I think actually you probably could. We haven't. But that's kind of the next step. This will be actually up on the archive probably in the next couple of weeks or so, if you guys are interested.
Let's see, one more question, and then maybe after that we'll...
Yeah.
You said there are an infinite number of these transformations. Is that smoothly infinite, or is it just you keep on trying it, keep on getting different ones?
Yeah, so I use infinity here loosely. In fact, there's no rigor in any statement about any of these neural nets. Not just from me, but really from anybody. So all I know is I retrain, it finds another model, it looks different than the other one. And you just keep doing this, after you do it several hundred times. We did one neural net where we trained, I think we did 2,000 realizations. And we collected statistics, but it's just every single realization is quite different. And they all perform the same. And so you're kind of in this situation where, like I did 2,000 neural nets. They all look completely different, but they all give me the same result. That's somehow saying something. But, whatever. It might be interesting even to prove that there might be an infinite number of representations, right? That could be something that somebody could do someday. But it's a very loose statement on my part.
All right, let's thank our speaker again. Usually we have a reception after these Boeing seminars, but obviously we're not in a position to do that yet, hopefully in spring. And I want to remind you that we have a second Boeing seminar 14 days from now, when Jonathan Mattingly from Duke University is going to talk to us about mathematics and Boeing and very